Before we get to work discussing indeterminate forms and ultimately L'Hopital's rule, I just wanted to show you one last thing in Mathematica. Now, Mathematica is super powerful mathematical software, and limits are a thing that mathematicians are very frequently interested in. So if all we cared about from the previous exercise were the answers to the problems that were originally posed, we could have sidestepped all the work we did previously with graphs and tables and just asked Mathematica to compute the limit of the expression as the variable approached something specific, and Mathematica would have given us the answers that we found previously. I didn't do that, however, because I wanted to get us thinking about indeterminate forms one little bit at a time. So, the purpose of the previous exercises were to show that if we have some sort of function, and we know the limit as x is approaching some specific value of that function is infinity, and maybe we have a constant, or maybe we have some other function who, as x is approaching that specific value, is approaching a constant. If we then go consider the limit of the quotient of those two things, we're going to end up getting 0 if this limit is infinity and this c is a constant. Because, like in example 3 in the previous video, eventually this function will outgrow whatever this constant is. And as soon as that happens, we will end up having a fractional thing here. It's getting smaller and smaller and smaller the closer this gets to infinity. And that's going to make the whole thing trend towards 0. Examples 1 and 2 were showing what happens if we have a function as x is approaching something, g of x is approaching 0. If we then go consider a fraction, we have a constant on top, and g of x is getting very small, then this fraction is approaching some type of infinity. Maybe positive infinity, maybe negative infinity, and so that can create some issues on, does the limit even exist if, as we approach from different directions, I'm getting different infinities? Or will the limit be one of these two values, plus or minus infinity, if the limits match? So we had two different things that could happen in this case. It was a little bit more challenging, but the concept is, if I try to, in quotation marks, divide by a constant by infinity, what that means is I'm taking a constant number and dividing it by something very large. If we're trying to quote-unquote divide by 0, we have a constant, and then this denominator is getting very small. That will ultimately make this function very large in absolute value. So we took the time to do that example in great detail because sometimes calculus students see limits with a 0 or with an infinity, and they just panic. They throw down one of those values. 0, infinity does not exist. And really what we should be thinking when we see zeros and infinities is that we need to take our time and be cautious. Things get even more complicated when we don't have a constant in the numerator. Things get more complicated when I have maybe two functions, both of which are going towards infinity around a specific value, or both of which are approaching 0 as we approach a specific value. The way to properly think about limits in that situation is, what's happening as I approach a value if my numerator is very large, but my denominator is also very large? What's happening if I'm approaching a specific value and my numerator is getting very small, but my denominator is also getting very small? That's complicated because what's really important is the relative largeness or smallness of the numerator to the denominator. If both numerator and denominator are very large, but the numerator is much larger, this limit could be large. If both numerator and denominator are large, but the denominator is much larger, this could be very small. And because of the fact that it's complicated, the formal mathematical word for big over big or small over small would be an indeterminate form. I might call it mathematical garbage, or I might call it something that's confusing. It's something that requires thought. It almost feels like it could be anything. which is true. And so this is when we have this, and so when we have this situation with indeterminate forms, we're going to have a very powerful weapon for dealing with those indeterminate forms. And that weapon is L'Hopital's rule. So I've created the statement of L'Hopital's rule for us right here. I'm not going to read word for word everything it says, but I'd like to give you the idea. Let's assume we have two functions that we are able to differentiate, and let's assume that when we're taking the limit as we approach some specific number, that we get one of those indeterminate forms, small over small or large over large. And I'm going to allow for negative signs. I didn't list all possibilities here, but having a minus sign in numerator and denominator is just fine there. What L'Hopital's rule tells us we can do is it says that the value of this limit, this indeterminate form, 0 over 0 or infinity over infinity, it surprisingly has the same value as another limit that we might be able to compute with different means. And that might help us make sense of what this original limit is. The limit that surprisingly has the same value as our original limit is the limit as x is approaching the same thing of the derivative of the numerator divided by the derivative of the denominator. So L'Hopital's rule is a very, very powerful technique. We need to be careful when we use it, and in future slides and videos, we will explore examples of using it and not using it. We have other techniques for finding limits, and it's important to remember that, but L'Hopital's rule is a super powerful technique for evaluating limits of things, and we'll play around with that in the next video.